All right. So checking this new setup with Streamlabs and see if I'll get back to streaming. So I'm working on this thing, which is basically I want to do like a Shazam yourself with self-supervised learning. The idea is that I want to be able to find a song from like maybe you just remember a few lyrics or just like the melody, whatnot, and you should be able to give this as an input to the model, and the model will find the best matches from the library. So I'm starting with just a few songs that are like top hits on TikTok, because I guess this is these songs that you have in mind, but you don't know the titles. Anyway, to do that, I want to use this architecture, which is this simplest one for self-supervised learning on images. So the idea is very simple. Let's say we have a song X. We're gonna take this song X, and then we're gonna have a set of different transformations. So it could be trimming, adding noise, whatever. These transformations are called capital T, and so for each song, which is a sample here, we're gonna draw two different transformations, which will give us x1 and x2. After two different transformations, we're going to pass these two transformations through an encoder. Here, the encoder is a ResNet. We're going to get a vector z, z1 and z2, and then we're going to project with an MLP to a final projection vector, and then we're going to use a contrastive loss between these two and the other negative pairs in the batch. So we're going to take the two output here and the two output of a different song, and in the whole batch we're going to be able to compute a contrastive loss to make sure that we are learning similarity between songs. Hopefully this should work. But in our case, it's a bit different because we don't have images, we have songs, and so what I'm doing that I'm using spectrograms. So I'm pre-processing the audio clips from the music library, and then I'm computing the spectrograms, the MEL spectrograms of these clips, which gives me images, and then I'm applying the technique described above on these images. So I've built my custom dataset with Pytorch, and the idea here is that because the song is very long, one of my transformation that I'm always applying on both is a random crop. So I'm taking random 10-second clips from X, which means that X1 and X2 might correspond to different moment of a song. So that's what I'm doing here. Basically, cutting these clips beforehand so that it's less expensive. So yeah, that's the idea. The idea is simple. When you take a sample from the dataset, what I do is I get the song at this index, then I retrieve all the clips. I select two random clips. Here I'm not doing it random because I've had some problem, but later on I'll do that. So I'm taking two random clips from that song. then I'm getting the signal corresponding to that song, and then I'm doing the pre-processing, which is a mix, so like resampling, cutting, and then also mixing the different channels, because you can see here we have different channels, and I want just one single channel, and then I'm getting the spectrograms, and I'm returning these two things. Okay, so here it's x1 and x2. Next we have the model. The model is very simple. Again, it is a ResNet. Here I'm using a pre-trained ResNet, and I'm just adding the first convolutional layer because my images have a different shape, and to fine-tune this ResNet, I'm changing the last fully connected layer, and then I have the projection layer and the forward function, and that's it. So just to make sure it works, I'm instantiating the model, I'm running it through a first batch, and we indeed get the right output. So this is just the shape. 7 is because we have 7 songs in the library. This is a full batch, and 256 is the length of the output vector, which might be too big, but anyway. Yeah, that's the ID, and then I'm having all these different utility functions to do the training, but now we are getting in the tricky part. It doesn't really work that well. So here I'm training it again. I only have seven songs. I'm training 1,000 epochs, and the loss is not really decreasing. It's not stable at all. I'm computing recall at 1, 2, and 3. As you can see, it starts off pretty well. Sometimes it even starts at 1 everywhere, which is great. But then it decreases over time, and then usually it would converge to these values for the recall, which I'm not sure I fully understand. So yeah, that's pretty much it. What I've done here, the very end, is okay. Yeah, I took another song, which is where is it? Okay, yeah, here. So I took another song, which is a song from my library, but this clip is a slowed down version. So I'm doing the same pre-processing here. So as you can see, I'm using the same exact methods from the dataset to get the signal, to do the pre-processing, which is resampling, mixing the different channels, etc. And then I'm getting the spectrogram, I'm getting the output, I'm feeding the spectrogram through the model to get the output, and then I'm finding the best matches in my library. Now the thing is, this test clip is actually what you know about Valve. It's at the 4th position, so that's a problem. So there are a few things we can do. The first thing we can do is make sure the loss function is implemented correctly with dummy data. So we can do something like normalize trusted loss on what we can do is torch dot no, not cat tensor. Basically, the idea here is that you're gonna have two things. Yeah, so 0, 0. Let's say we have something like this. And then usually we have the temperature, right? 0.1. I think I already have the default value. Okay. Right. So what does this mean? So this means, maybe this is a bad example, so let's add more to it. Okay, so what you're going to have is something like this. Okay. These are the first two vectors. And these, okay. So let's say that, for example, this one is the first z, z1, this is z2, and then this is the same thing but for a different song in the batch. So I'm concatenating them. Maybe for this one I can say 1, 0, 1, and 0. So this is an ideal situation, and the loss is like that. But if I do this and let's see, 0, 1, okay. Let's go back to the space here. The loss is the sum. Let's get it here. What is the loss? What's this? Okay, so let's do it here. Okay. So let's say we have z1 equal to 0, 1, 0. We have z2 equal to 0, 0, 0, 1. And z3 is 0, 1, 0, and z4. Okay, that's perfect, right? That's what we would like to have at the end. The similarity matrix is going to look something like this. I would 10 because tau is 0.1. This will be 1 and 2, right? 0, 0, 10. No. I'm missing something. Yeah, because it's going to be longer than the. Okay, yeah. So yeah, 1 and 2, 1 and 3 is going to be 10 as well, and 0. And then here it's going to be like this. Yeah. And then we can just repeat. 3 is going to be 1, etc. Yeah. So this is our similarity matrix divided by tau. Oh yeah, I got. Wait a second. No, yeah. Yeah, that's cool. What we have next is this right here. So if we do, let's try. Let's try. Let's we have this. Now what we want to do is let's define L as minus log np dot log of np dot sigmoid np dot x of sim I j, right, divided by yeah, that's exactly it. This is divided by np dot x sim I j. Okay. If so 4k in range 4, and so I'm going to say if k is different than I, else 0. Yes. Okay. I might have to do this. Alright, that sounds great. Now, we want the loss, it should be equal to np dot sum of L 2 times k, 2 times k minus 1 is this, for k in range 2, divided by 4. How does this sound? Great. What we have, alright, and if I do normalized interest launch that tensor. Z1, Z2, Z3, Z4, type, touch, float, and temperature, let's specify it. By the way, this is 0.1. Cool. Here. Okay. That's great. It's done. Okay. Okay. And this and so. All right. And that, yeah, it's not the same. We have a problem with loss. I can this to me feels weird, like the fact that you're using torch.zeros. I don't know, that feels weird. You know, to be honest, yeah, let's try to write out a function, okay? What's it called? It's empty. Let's call it like this. Yeah, empty. Plus, we're gonna have one equals 2 and temperature. So put one, okay. The first thing we're gonna do, let's take some of these anyway. The first thing we're gonna do is this. So we're gonna say one egg normalize. Gonna do that. Second thing is the similarity matrix. It's gonna be close one. That's the thing here. If you want to keep the similarity matrix, I feel like you're gonna have to concatenate all of them. So let's concatenate these. Yeah. Let's say sections. Punch.get. Punch 1, punch 2. projections key. So we have our similarity matrix. We've normalized this so it's good. And then if I divide by the temperature now. So we are good. And then the next thing is that we're gonna have to remove the diagonal at some point. But let's not do it just yet. What we really want to do is minus torch.log. We want to compute this, right? This thing here. And this is just torch.text of the similarity matrix, right? Divided by the should we do the sum or it's over all the other okay, yeah, I see. This is going to be a mask. This is where we use this here. Use the mask, and then he gets the positives and negatives. But I feel weird about these labels because this is equal to 0. If I can labels here, labels are known. Yeah, so this is weird. And then the temperature, he's doing it here. Oh yeah. How about the let's what these logits are. Oh, they're great actually. 10, 10. So why do I have only 3? Oh, I'm missing a vector. That's good to know. What happened? Oh, he removed the diagonal, right? So I don't have the last one here. Here I have 10, 0. I don't have the diagonal, and then 0. Here I have 0. No diagonal, 0, 10, and then 0. This is 10. Okay, so this is the similarity matrix without the diagonal. But then you're missing this, right? No, because we're never gonna. Here we're doing this, so we don't even need. Okay. Get it. But I feel like is it me or is there a problem with this implementation? Oh yeah, it's me. Wait, I don't know. I think it's the same. Yeah. It should. Uh, I don't know if it should be the same or not. Oh, but the way I'm indexing them is not the same thing. Like, yeah, um, in my case, is in the paper they're doing 2k minus 1. So they've been doing like z. In my case, z3 and z1 are actually the same, right? But in the paper, z3 is z2, and so these are consecutive indices. And so if I want to match that, what I need to do is, yeah, I need to say k and k plus 2, and here k plus 2 and k. Nope. I feel like I'm missing something. You know what? To verify that the implementation matches my way of doing things, I could print positives, negatives, print positives, negatives. What? Oh wow. Okay. So maybe this should be 2, right? Okay, so the loss is definitely wrong here, and we have our 4. What the hell? Find this here. Okay, why not? CCLR not by. Yes. So this is the model, and this is the loss. This is wrong, right? This is wrong. Select only the negatives. Select and combine multiple positives. Doesn't feel right. I don't actually, you know what? This looks great. Because we have something that's close to 0. Like, I could try with, something like this, right? Like, what if I swap things and I to say that okay, I get that it's confusing, so let's actually change that and say that Z2 is this and Z3 is that. Yeah, that's, I think that's fair. Let's compute that. Oh, I haven't changed the connection. So what I'm going to say is that no. I don't know. Spend some time. I sit down and think